My name is Stuart Simmons, and I'm one of the geoscientists on the JTAHFORGE team. This presentation is a brief introduction to the geoscience of the JTAHFORGE site. In addition to setting the geological scene, I want to bring your attention to a wide range of data sets that are accessible through the JTAHFORGE website. This work represents the collective effort of a large number of individuals, and the contributors are listed below. The outline of this presentation covers the JTAHFORGE website and datasets, location, geological setting, heat flow and thermal structure, reservoir lithology and fracture patterns, groundwater and fluid compositions, and geochemistry. Let's start with the website. This is the home page, which is the access point for information about JTAHFORGE. There's a lot of information on this website, so please take time to explore it. But for information on research findings, follow the orange arrow and click on the research link. That takes you to this page, where there are 6 additional links to various types of information, datasets, and apps. Geoscientific Map takes you to an ArcGIS online map hosted and maintained by the Utah Geological Survey. Here you can look at various datasets from the project in a conventional ArcGIS format with layers that you can turn on and off. You do not need ArcGIS to run this app. It is all web-based. Seismic monitoring takes you to the University of Utah Seismograph Station's webpage that is dedicated to monitoring seismicity around the JTAHFORGE site. Modeling takes you to the Earth model, which allows you to visualize the 3D attributes of the JTAHFORGE site and the subsurface. This is a leapfrog application which Sequent is providing to the JTAHFORGE project. This tool complements the ArcGIS Online map tool, and combined they provide unique perspectives that are worth examining. The research link takes you directly to the Geothermal Data Repository, which is hosted by the National Renewable Energy Lab. Here you will find raw datasets and synoptic reports covering the work that have been carried out at JTAHFORGE. These include well logs and data on rock properties that have been acquired and used for analysis. The last item to direct your attention to is access through the drop-down menu. Go over to Project and go down to Publications and click, and that takes you to the Publications webpage, where you will find a list of publications produced by the JTAHFORGE project. Under 2019, you will find the link to the Utah Geological Survey publication 169. The bulletin comprises 14 papers that covers various aspects of investigations up through early 2019. It is all open access and available online. This too is where you can find a plate showing the geological map of the region surrounding JTAHFORGE. In the slide below, a small part of this map is shown. JTAHFORGE is located in southwestern Utah, about 3.5 hours drive south from Salt Lake City, represented by the star. The site is reached driving south on Interstate 15. From the intersection with Interstate 70, JTAHFORGE lies about 35 kilometers to the west. Over on the right is a close-up of the JTAHFORGE site. The T-shaped outline is entirely located on state and private land holdings. The other labeled features are referred to below. This Google Earth image looks north and provides a perspective of the whole northern Milford Valley. The JTAHFORGE site is located here, and it is about 5 kilometers west of Roosevelt Hot Springs, which is located here. You can see the Mineral Mountains and its northern extent, and the town of Milford. The regional understanding of the basin architecture is known from gravity and seismic reflection data, and interpretations are shown in the next slide that follow these two east-west transects. The upper cross-section interprets gravity data, and the lower cross-section is based on a legacy 2D seismic reflection survey. Both sections show the distribution of low-density basin fill sediments and basement rocks, which on the east side of the valley hosts the JTAHFORGE EGS reservoir. Now, before going into the geology, I just want to give you an overview of the site. This view looks to the northwest, and it shows the settings of all the wells drilled so far, the road access, and a newly installed power line. 5832 is a vertical well that was drilled to 7,500 feet in 2017. This is the site of the stimulation experiments that took place in both 2017 and 2019. Well 6832 is vertical and drilled to about 1,000 feet depth, and it has been instrumented with 2 downhole seismometers. Well 7832 is also vertical and drilled to about 3,300 feet depth. It has been instrumented with a DAS fiber, and it was used to deploy a vertical seismometer array that was used for the 2019 stimulation experiment. This well can be re-entered to deploy additional sensors downhole. Also shown are sites for other proposed wells. 5632 is a proposed well for seismic monitoring. 16A 7832 is the site of the first deep injection well, and the dashed line represents the trace of the directionally drilled leg through the crystalline basement. This slide shows the geological setting of the JTAHFORGE site as represented in plan and cross-sectional views. The cross-section runs in a northwest-southeast diagonal across the map. There are 3 main elements to emphasize. 1 is the rock types, 2 are the fault structures, and 3 is the thermal structure. So there are 2 main packages of rock. The JTAHFORGE site is located on young alluvial fans shed off the Mineral Mountains. These represent the youngest sediments making up the package of layered and horizontally bedded sedimentary rocks that form the basin fill sequence. In green, the crystalline basement is mostly made of Oligocene-Miocene age plutonic rocks that are collectively referred to as granitoid. Other lithologies include rafts of Precambrian gneiss that are engulfed by the granitoid. These are exposed in the western foothills of the Mineral Mountains. There are also young Pleistocene rhyolite flow dome complexes that represent the youngest and most recent phase of igneous activity, and these date to between 0.5 and 0.8 million years. Structurally, there are 4 main faults. The best known is the Opal Mound Fault, which extends for about 7 kilometers. This is a normal fault with a very small offset of about 15 meters as inferred from the topography. However, stratigraphic markers are unknown, so this is just an estimate. The south end of the Opal Mound Fault is marked by a deposit of silica sinter that formed from the discharge of hot boiling chloride water about 2,000 years ago. Currently, there is no evidence of surface thermal activity in this vicinity. Instead, most of the surface thermal expression is limited to the north end of the fault, where there is a patch of steaming ground. There is additional evidence of surface thermal activity in the central part of the production field, and this takes the form of warm ground and a few steam vents. The main thing is that the Opal Mound Fault marks the western boundary of the Roosevelt Hot Springs hydrothermal system. The NM fault trends east-west, and it is mappable where it transects a deposit of alluvium on the northern side of this east-west trending valley. It is projected to extend westward at least as far as the Opal Mound Fault. A series of small offset scarps cutting the young alluvial fans, forming linear and branching strands, are collectively known as the Mineral Mountains West Fault System. This fault system extends in a north-south direction south of the Utah Forge site. The fourth fault is unnamed, and it is most easily recognized as the contact between the basement and the overlying basin fill. This feature started out as a high-angle normal fault that was important in accommodating extension across the North Milford Valley when the Mineral Mountains were undergoing rapid uplift and exhumation, which occurred between 6 and 10 million years ago. The modern orientation is attributed to rotation and tilting, and it is believed to be inactive. Now, the thermal structure is represented by isotherms, and this is a key feature of the site. The thermal structure has been interpreted from a number of temperature gradient wells and heat flow studies dating back to the late 1970s. The modern state of understanding has been analyzed by Rick Alice with the help of his colleagues, and their results are reported in a paper in the Utah Geological Survey publication 169, which I referenced earlier. Beneath Utah Forge, the thermal gradient is mostly linear, as represented by evenly spaced isotherms. This indicates solid-state conductive heat transfer, whereas east of the Opal Mound Fault, the isotherms are bunched and the temperature gradient at shallow level is very sharp. This represents heat transfer due to hydrothermal convection. This slide summarizes temperature gradient data collected from deep drilled wells. Hydrothermal convection is represented by the profile over here that is labeled Roosevelt Hot Springs. This is based on downhole temperature gradients measured in production wells that feed the Blundell power plant. Beneath the Utah Forge site, temperature profile in 5832 is linear, increasing steadily with increasing depth at a little bit greater than 70 degrees C per kilometer. The maximum temperature is at the bottom of the hole, and it has a value of 199 degrees Celsius. Again, this even temperature gradient represents heat transfer by solid-state conduction. At shallow depth, there is a slight bulge in the temperature profile, and this is due to hydrothermal outflow from Roosevelt Hot Springs that is heading towards the middle of the basin through a shallow aquifer hosted in the basin fill alluvium. Representation of heat flow is portrayed as isotherms at 200 meters depth in this map, and then in the next slide at 2 and 3 kilometers depth. These maps provide a three-dimensional understanding of the thermal structure around Utah Forge. The hottest temperatures are associated with the Roosevelt Hot Springs hydrothermal system. The shapes of the isotherms here indicate outflow basinward around the north end of the Opal Mound Fault. Additional minor outflow occurs around the south end of the Opal Mound Fault. These are the other two maps that I was referring to at 2 and 3 kilometers depth. Combined, the maps provide a high-quality, three-dimensional understanding of the thermal structure over a fairly large region encompassing the Utah Forge site. Additional data sets providing 3D information about the geological structure comprise a high-resolution gravity study and a 3D seismic reflection study. These data have been used to characterize the dip on the contact between the basin fill and the underlying basement rocks. You can see the prominent reflector which marks that contact. In this image, you can see both the geological and thermal structure beneath the Utah Forge site. It includes a depiction of 7832, which has a bottom hole temperature of 110 degrees Celsius. Also, you can see the slight undulation in the basement contact, which has been detected from analysis of the 3D seismic reflection data. Turning to well 5832, data from here provide the best characterization of the EGS reservoir. In the following few slides, I will limit description to rock types and fracture patterns. For background, and since being drilled in 2017, this is a graphical summary of activities in the well. So drill cuttings were collected over the full length of the hole. Temperature and other geophysical logs were obtained, as was an FMI log used to detect and characterize fracture patterns. Drill core was taken from 2 intervals deep in the hole, and stimulation experiments were run in 2017 and also 2019. This slide represents the stratigraphy and rock types that have been found beneath the JTAHFORGE site. Over here is the chipboard log from 5832. The color variation represents the different types of rock that were encountered as this hole penetrated, first in the upper part through the layered basin fill, and then in the lower part through the crystalline basement. The contact between the 2 units is about here. You can see the color variation in the basement, which reflects different phases and different types of plutonic rock. The mineralogy has been characterized over here, and on the right, intervals of drill core are shown, and these were obtained from the deep part of the hole down here. The light color reflects granite, and the medium gray color represents diorite. In the bottom right corner is a thin section view showing the interlocking grain boundaries that are responsible for the very low porosity in this rock. This slide additionally shows the chipboards from wells 6832 and 7832. Here is the basement contact. And I also want to draw your attention to thin section views of cuttings showing cataclasis and shearing along fractures in the rocks in the upper part of the basement interval. These occur very close to the contact with the overlying basin fill. Similar deformation fabrics were seen in the upper part of the basement in well 5832. An FMI log was obtained after completion of well 5832. Here you can see it stretched out through the hallways of EGI, and this provides the best characterization of the fracture patterns and fracture orientations in the basement rocks. The StereoNet on the left represents an upper hemisphere projection of the poles to fracture planes identified in the FMI log. Importantly, fractures are moderately to closely spaced, and they have a wide range of orientations. Mirroring the FMI log data are the measurements of fracture patterns in outcrops in the mineral mountains. Exposures of the reservoir rocks in the mineral mountains is one of the important assets of the JTAHFORGE site, and these data have been used to inform modeling and simulation work performed by a team of modelers led by Rob Pagorny. In detail, mineral mountains outcrops show 3 main orientations, which are shown in the photographs. One fracture set runs east-west, and you can see this in the lower photograph, where the fractures are closely spaced, subparallel, and near vertical. The other 2 fracture sets represent a conjugate pair. One has a very steep dip that is near vertical, and the other that has a dip that is inclined at a shallow angle to the west. The azimuth of this conjugate pair is north-northeast, south-southwest. John Bartley has synthesized the evolution of the fracture patterns into a time series model. The upper panel represents the early onset of extension after much of the plutonic rock had solidified, with the development of a conjugate fracture set. The middle panel represents localization of fault development and normal fault movement along a single fracture plane. The lower panel represents the effect of uplift and block rotation accompanying tectonic extension. This feature here represents the contact that separates basement rocks from overlying basin fill. This other structure represents one that is analogous to the Opal Mound Fault. A number of wells have been drilled around the JTAHFORGE site. Some are used for geothermal production at Roosevelt Hot Springs to supply the Blundell power plant. Others are used for groundwater supply in the central part of the North Milford Valley. These wells are all marked on the map on the left, and many of them have been sampled and fluids have been analyzed, and these permit characterization of groundwaters around the project area. First, I want to draw attention to water level data, which are used to map the piezometric surface in the water table. These are represented in blue lines, which are contours on the water table. In the vicinity of the Opal Mound Fault, this gradient is particularly sharp. Wells in Roosevelt Hot Springs, prior to the commissioning of the Blundell power plant, had pressures that were 35 bars higher than wells on the west side of the Opal Mound Fault. And this corresponds to a step drop in the water table of more than 300 meters from east to west across the fault structure. From this, we deduce that the Opal Mound Fault is the western boundary to the Roosevelt Hot Springs hydrothermal system. Turning to the geochemical data and the graphs on the right, there are three types of water: the deeply circulated geothermal water produced at Roosevelt Hot Springs, basinal groundwater, and meteoric recharge. These are isotopically and compositionally distinct waters, and they allow for the tracing of shallow fluid flow down gradient from Roosevelt Hot Springs westward into the basin. The meteoric recharge, represented by rainfall and snowmelt, mostly falls in the Mineral Mountains. Outflow from Roosevelt Hot Springs makes up the groundwater in the shallow aquifer directly beneath the JTAHFORGE site. This water is non-potable owing to high total dissolved salts and elevated boron concentrations. As JTAHFORGE will require a water supply for drilling, stimulation, and flow-through experiments, preliminary assessments of the effects of high-temperature water-rock interaction have been modeled using different starting compositions based on locally available groundwater. Mineral deposition results in all the calculations, which is not surprising given fluids will be subject to considerable heating once injected into the reservoir. Much more work on this subject is required. Well, that brings us to the end of this brief presentation on the geoscience of the JTAHFORGE project. It covers just one facet of the project, and interested viewers are encouraged to explore the website for links to other data sets and reports. This project is sponsored by the Department of Energy. Additional support has been made available by state and local government agencies and local landowners.